Afternoon, everyone. Uh, Here today we have a webinar on introduction to recommendation systems. The session is going to be conducted by Mr. Yash Vaishnav, who is a AI/ML engineer in web occult technologies. Sir, it is an honor to host you here, and I would request you to please start the session.
Thank you so much, sir. Hello, everyone. Myself, Yash Vaishnav. Today, this session is going to be about recommendation system. Uh, Before we begin this seminar, I'm going to assume that most of you guys, or at least uh, 50% of you guys, are familiar with the term machine learning. We don't really need any in-depth knowledge for this seminar. The thing is, you should know what machine learning is to begin with the seminar. So, about me, I'm Yash Vaishnav, as I introduced. I'm AML engineer at Web Technologies. I'm also an alumni of Par University. So now, first question is, what really is a recommendation system and why we are studying it? The recommendation system starts from your nearby stores. If you go to a store, you ask for a pair of shoes. The shopkeeper will give you the shoes as well as he will give you a pair of trousers and shirt as well. Now, if you go to Amazon, uh, Facebook, or YouTube, you will see these algorithms are being used on a great scale. Now, the thing is, uh, recommended systems are the only systems that are, growing a company or growing an organization because their products, what they want to deliver to a user, should, you know, reach the correct audience. Uh, it is an information filtering system that helps user information that will be helpful with their relevant interests. Now, they are known as the salesperson of the internet. If you click on YouTube's one video, you will see other videos similar to it. They will say recommended to you by YouTube. Okay, so the companies that use these recommended systems are like Netflix, Facebook, Amazon, LinkedIn, eBay.
Sorry to interrupt you, Yash. Could you be a bit louder, please?
Oh, sure. Okay, so this system really benefits the companies as well as the users. Suppose you are searching on, you are streaming online and you don't really find the right content. So you won't really visit those website again. Okay, if you go to YouTube, you are searching for some uh, stand-up comedy meme, stand-up comedy material. What will happen if you search stand-up comedy and you find news or debating? The system don't really work like that. So companies really need to focus a lot on recommendation system as well as because it helps in impacting the users' interest in the website. Okay, so the Amazon's revenue, which is 35% of the total revenue that Amazon earns, is from recommendation system. Spotify, on the other hand, earns 33.3%, which increases monthly. Okay, on YouTube, which also provides a greater extension for this recommendation system. Best Buy is another company which has an increased revenue sales due to recommendation system. Now, what used to the recommendation system that we are saying doesn't exist really on internet. It exists everywhere. It exists in your day-to-day life. Earlier, most recommendation systems were based on user rating system. You can say like uh, if you go to Amazon, you purchase a product. After purchasing the product, you will see ratings. You rate the product from 0 to 5. But those systems really didn't contribute much to the program that we are developing. Why? Because it can be altered. If you purchase some product, it might not necessarily that the product was made for you or the product really mean to you. You could just give negative feedbacks or anything. You can alter the user data. So most of the companies that we see currently, and we are seeing the issues that they started to gather user data. These user data are really gathered to show uh, what are your interests like based on your history or your search history preferences. The company or the website will look upon your activities and check whether the product that they are going to show to you are useful or not. So, what kind of data do we give? Is primarily the main question. Like, how do we give our data to companies or to anyone. There are two kinds of data. One is explicit data, another is implicit data. Explicit data. Over here, when a user or a purchaser buys a product and then gives his true opinion, for example, Amazon, you buy a product, you give your opinion, you comment, you rate how you feel about the product. That's explicit data, where the user know he is giving his data to the company. What is implicit data? When a user looks at a product but doesn't merely clicks on it or purchase it, it is implicit data. And the form of implicit data can be told as you can see when you search a particular query. Let's say we are searching for an algorithm on Google. You will see tons of websites. The website that you click will have the implicit data of yours, which means that the user has clicked on a website because he has been interested in a website by reading a content or something. So, which data should be collected? Now, if you are clear with this thing, explicit data and implicit data, I would like to ask a question to you guys. Uh, why one should use explicit data and why one should use implicit data? Both of the data really have their own advantages and disadvantages. The thing with explicit data is it is difficult to collect. For explicit data, you need to sell your product to someone, which involves a user purchase, and then you need to get their feedback. Even though the user will purchase the product, but they won't really give feedbacks to your purchase. So it is difficult to collect. Also, uh, the thing with it, the positive part of explicit data is you don't need to pre-process your data. What pre-process really means is most of the times when we work on data, we have noise in our data, unwanted thing that we don't really want to calculate or that doesn't contribute any growing. So straight away companies, they don't really appeal to most users. So explicit data is hard to mine, but it's easier to process. Implicit data. In explicit data, user can rate the product from 0 to 5. Now, if someone rates the product 0, the overall impression of the product goes negative. Whereas if someone rates the product positive, the impression of the product goes positive because that same thing can be visible to a lot of users and it affects their sales. Now, implicit data is generally based on clicks and views. User cannot give negative feedback as if we told we are searching for some algorithm on Google. Let's say we are searching k nearest neighbor algorithm. Now, there are 4 to 5 websites, and out of the 4 to 5 websites, I click on the first link. No one knows, I mean, by the users. No other users know that I have clicked on the first website. But the company knows by the traffic that yes, someone has clicked on our website. And if the company alters their biodata or information about their website and they don't get any clicks, they would get the negative feedback that yeah, from changing this thing, our website are not getting much clicks or views. So implicit data is good in terms of not providing a negative impression to other users. The thing with implicit data is it is noisy, but you get too much of data. Like too much of window shopping users are there. They will just visit your website and they will just go back to their own. They will go to some other website. So it corrupts the damage. If you have so much noisy data, but also you have too much data, which will corrupt the drawbacks of it. Now, implicit data, it really needs the confidence matrix because there can be some particular amount of data, let's say 30% of the users that were genuinely interested in our website, 70% of the users that weren't actually interested in our website, but just clicked on the website by any false means or anything. So we need a implicit data to have confidence matrix. A confidence matrix is something that says whether the data that we received is true or not, or it is useful to us or not. Now, after knowing about explicit data and implicit data, let's say we mined our data, we got tons of data. Now, all those processing, creating those algorithms and then sorting and pre-processing your data. It takes time. But after pre-processing all those information, you need something where you can feed your data in. It can be a model. In machine learning, model is something where the numbers or the vectors they both have some similarities which makes sense to a user. Let's say if I provide an image to a machine and it tells me whether it's a cat or a dog. So I provided data, and the data has been represented in binary form or zero ones or in a vector space. That thing is useful in the output part, whether it's a cat or dog or not. Now, latent model factor. What is latent model factor? The thing is, uh, there's an assumption that exists a user space, uh, a low-lying user space, where there are tons of users with tons of taste, different expectations. Like my taste for music might be I like hard songs, I also like rock songs, I like soulful songs. It doesn't really mean that the same taste could be of any other, right? So latent model factor helps us with dividing the users with their taste. Okay, so yeah, this is latent model factor. It surely is complex. It is complex. Okay, so we won't hurry much into latent model factors. The latent model factors really use matrix factorization. What factorization do is, uh, you see this users and these songs. The rows represent users and the column represents songs. Each user will be rating their songs. Let's say there are 1 to 10 columns, each with the song title, and there are 1 to 10 users, each with their names. Each user might have rated a song, and based on that, we can find that the user profile, wherein all the users and the songs, these are two factors that affect the combination of this matrix. Okay, so the user profile with a dot product of the song profile, wherein all the songs are there and all the users are there. We make a dot product and we'll find how close each of them are associated. So we will be, recommending the same songs or same movies to someone else. To get a more clear idea, we'll just follow some basic examples right now. So in latent model factors, you will see two kinds of filtering. One is content based. Now, what a content based is, it requires some good amount of information. Like if I'm talking about a movie is my product right now. I need to know its features. What are features? Features are the ID, the name of movie directed by, the actors in movie, the release date, the gross amount they earn. These are features of a movie. It describes what this movie is. All right. So as you can see, this working on movie recommendation system. It uses information like genre, year, actor, or director. Now, user preference from the most useful feature and comparing it with similar user preferences. Let's say there are two users, A and B. Now, A likes a particular movie. Let's say A likes Jumanji, it's a film, and B likes the same movie. Now, what content based does is, if A sees a new movie, let's say Toy Story, uh, the same movie will be recommended to user B because A and B had a same similar preferences matched earlier. Now, the problem with content based system is, if you go to your YouTube, all right, you click on some particular website, some particular videos, some serious kind of videos, some political issues or something like that. YouTube will always show you those videos if it is based on content, because from your past, you have been clicking on the same kind of uh, you know genre of your videos, serious ones. You will in future you will be seeing the same content, and this will affect the users working on the website, the users interacting with the website. So we don't want it. So we introduce another user's preference, the similar taste. Let's say two users are having the same taste. If the second user sees something new, it will be recommended to the new user. Also, now there's collaborative filtering. Okay, uh, collaborative filtering includes a large amount of users. Let's say there are 50 users, and everyone has watched five film at least in common. If there exists a new user, which is 51, so based on their preferences and their rating, the new user will be shown the recommendation of a particular new film or not. Where multiple users' interests are known and recommendation will be given to the new users. All right. Collaborative filtering is usually has a higher accuracy because there exists a similarity in users. Now, uh, if you guys have any doubt, please ask the doubt in comment section, and our moderator will pass it to us. Okay. So this is a small table wherein we have the movie names in the column and the users in our rows. So we can see there are four movies: Men in Black, Apollo 13, Top Gun, and Terminator. There are two users right now, Emmy and Carl. Emmy has 5, 4, 5, 4. These are the ratings that Emmy provided to these movies. And similarly, Carl hasn't seen the movie Men in Black, but their tastes are similar. You can see Emmy has rated 4 for Apollo 13, and Carl has also rated 5 for Apollo 13. Similarly for these both movies. So the question is, should Carl be recommended this movie, Men in Black? Yes, Carl should be recommended the movie Men in Black because there exists a similarity between these users, Emmy and Carl. It's a very short example, but there exists a feature length of 10 legs, wherein there could be Men in Black, Apollo 13, Top Gun 2, Men in Black 3. So there can be many movies, right? As the number of column increases, the complexity of our algorithm also increases. But for this webinar, we will be keeping it up till 12 in upcoming slides. Now, uh, we are humans. We can see, right? 5, 4, 5, 4, and we can match with the similar users whether we should recommend it or not. But how will we be able to explain the same concept to machines or to programs who will automatically recommend the system? How will they know whether Carl should see Men in Black based on Emmy's rating and why? The thing is, there exists a matrix. Matrix is a form of measure that we use. Uh, let's say if I say I want to go to Vadodara from Ahmedabad, I will calculate the distance from here. It will be 150 kilometers. Now, if I say the same question, I want to go from Bharuch to Vadodara, it will be 80 kilometers around. So if I ask which one is the closer one to Vadodara, Ahmedabad or Bharuch, of course it's going to be Bharuch because of the distance. Similarly, similar kind of distance exists in machine learning. There are varied kinds of distance measures like Manhattan distance, Euclidean distance, Jaccard distance, Cosine similarity distance, and centered cosine similarity distance. For the purpose of this seminar, we will be using the last three, which is the Jaccard distance, cosine similarity, centered cosine similarity. Manhattan and Euclidean are used extensively in machine learning, but for this webinar purpose, we are using Jaccard, cosine, and centered cosine similarity. If you guys have any questions or any doubt, please write that in the comment section. At the end of the video, we'll be solving them. So do not get afraid of this. It's simple. Jaccard distance is all about A intersection B divided by A plus B minus A intersection of B. Let's do a small example to get familiar with this thing. Let's say you have two sets. Okay, before continuing more, uh, just keep focused on this part because it is the core part. We will be we will be having a hands-on session, and in the hands-on session, we will be seeing how these metrics are important in calculating, in recommending a movie. Okay, all right. So you can see we have two sets, set A and set B. Let's say these are the ratings. A user has given 1, 2, 5, 4. rating to a movie, and user B has given 2, 3, 5, 7. Now, what the car distance says is you need to take the intersection of A and B. All right. So the first part represents the same. You have taken the it is without replicate. All right. You combine A and B, and you get 1, 2, 3, 4, 5, 7, which is 1, 2, 5, 4, and 7. Because 2 and 2 is repeating, so we won't take 2. All right. And we will divide it by A intersection B minus A plus B minus A intersection B. If you do it in your notebooks, then you can see you will get this value 0.667. It says how close the user A and B have their interests. I mean, let's say user likes a particular movie, and based on their interest, they will be shown new movies. So this metric shows how similar their taste is in. There exists a Jacobian distance with duplicates. Earlier, you can see we used the set A and B, we merged them and we removed the duplicates. For example, 2 exists in both the sets, so we removed 2 and we took a common one. But with duplicate, you can see we are getting 0.75. We see an increased amount of confidence metrics over here, which says whether A and B, these both users are having the same taste or not. All right. So based on your application, it doesn't mean that using duplicates will always give you better result, or using no duplicates will give you better result. It depends upon the application that you are working on, and they both have their own pros and cons. All right, so let's try it with our larger data set. Let's say there are 4 users, A, B, C, D, and there are 7 movies, movies 1, 2, 3, 4, 5, 6, 7. Uh, what it does is we will be following the same approach uh, without duplicate one. We'll count the similarity between user A and user B, and then we will be counting the similarity between user A and user C. For user A, first of all, we need to count uh, the similar movies that they have seen. User A and B have seen a movie one. I mean, it's the similar movie that both of them have seen, and the total divided by 1, 2, 3, 4, 5. There are 5 movies total they have watched, and we have removed the duplicate, so there exists 5. If we take the duplicate Jacobian, which is this one, so it will be 6, but we are working with without duplicates. So the similarity matrix of A and B results to be 1 by 5, and similarity matrix of A and C results to 2 by 4. We are comparing the user A and user C. The common movies that they have seen is 1 and 2. 2 movies out of 1, 2, 3, 4. So it is simple. What it means to say is the number of movies they have seen in common divided by the total number of movies they have seen. Okay. After finding this, you can clearly see that the Jacobian distance, which is similarity of A and B, user A and B, is lesser compared to similarity of user A and C. But it's not necessarily true, right? If you can see, user A and B, they have seen two single movie, which is the movie one, and they have rated it 4 and 5, which means it is close to a good movie. And there doesn't exist any other movie that they have seen. And let's say if user B might have seen movie 4, just a second. Let's say if user B has seen the movie 4 and he rates it 5. So now our equation will completely change. What we want to do is we need to improve this system, right? Instead, similarity of A and C, the user A has rated movie 1, 4, movie 4, 5, and 1. And comparing it with C, you can see that user A says the movie 4 is awesome for him, but user C says it is a fair movie. Right? They have quite different opinion. Similarly, for user A, He rates movie 5 1, and user C rates movie 5 as 4, completely opposite. And yet our similarity matrix says that A and C have a much larger similarity in both of them, which is wrong. So there exists an improvement for this. We'll work on cosine similarity. In our 10th, 11th, and 12th, and even right now, some of you guys might be learning what our trigonometry is: cos, sine theta, tan theta. In machine learning, we use cosine extensively, and there exists a distance measurement, like the example of Ahmedabad to Vadodara and Bharuch to Vadodara. Cosine similarity is helpful when you represent two vectors in a high dimensional space. Let's say you have a vector. By vector, whenever I say what a vector is, it is a vector. The set is a vector. You can represent the set in a high dimensional space. All right. What a high dimensional space means is you can represent them in a graph form. All right. You can note down this formula. It's interesting. It will be used in our practical part that we'll be doing at the end. You take two dot products of two vectors, and then you take the cross products of them. All right. How do you take two dot products? Well, these are the two vectors, vector x and vector y. You multiply the first element of x with y and second with y second. Ultimately, you end up with a result 3. Now, what you do is you take the square and then you square root the final answer. You took the set x and you took the set y. You took their squares and you took their square root. You get 6.16 and 1. And after filling the information in your main formula, you will get a cosine similarity of 0.49. All right. We will apply the same in our, we will apply cosine similarity in this same table and we will find out the accuracy. Okay. This is the part where I think you will feel clear about cosine similarity. What cosine similarity means is this is our first vector, this is our second vector. How different are these? It depends upon the angle between the both lines. Let's say if these both vectors are close to each other, then the angle between them will also be close. And this is what we are getting in our cosine similarity. If the angle you get 30 degree, then it says that vector A and vector B are similar to each other. If the angle represents is 90 degree, then it means that there exists. All right. So
Yes.
uh, yes, yes, sir. Hello.
Your voice is breaking. Kindly repeat. Yeah, this cosine similarity example. Kindly repeat. Your voice is breaking.
All right. Okay. Thank you, sir. Okay. So for cosine similarity, uh, let's say uh, this is our vector A and this is our vector B. Now, when you represent these vectors in high dimension space or in graph form, you will see there exist two lines from the center, and these lines have a angle between them. The angle shows, let's say the angle is 30 degree. 30-degree angle will show whether both these vectors are similar or not. The lesser the angle, the more similar they are. If they both lie on the same line, it means they are completely similar. If the angle made by this line is 90 degrees, it shows that the vectors, vector A and vector B, aren't similar. The ultimate uh, meaning of cosine similarity is it will find the similarity based on degrees of these both lines. There's an in-depth explanation for that as well. I'll share the links with you guys at the end of the video. Now, another question for you guys. We know that using cosine similarity, we found this particular value, which shows how similar two vectors are, how similar these two vectors are to each other. Let's say it is 0.49. How can one find the dissimilarity, or can say, how can one find whether two vectors are not similar? The simple answer is you just minus it by 1. 1 minus cos of x comma y, which was 0.49. Uh, the matrix that you see over 0.51 shows how dissimilar these two vectors are. Uh, Upon your application, you will see whether to use similarity matrix in cosine or dissimilarity matrix. Dissimilarity helps you to know whether a particular matrix evaluates to a true form or not. Let's try cosine similarity with the same example as done in our Jacob example. To revise once again, we'll just go back. Okay, in Jacob, you can see we took the common value. For example, A and B, user A and B had a common movie that they watched, 4 and 5, and the number of movies they have watched together, 1, 2, 3, 4, and 5. Now moving to cosine similarity, we will see why it is better than Jacob similarity, Jacob distance. Okay, uh, in cosine similarity, we need to put zeros for the movies that the user didn't see. We have empty value over here. We'll be putting zeros or in all the non-watched movies. And what happens is you will get two values from this, 0.38, 0.32. Again, we calculated this based on our cosine similarity formula, which is the dot product multiplied by the cross product. All right. Now you can see the metric, the cosine similarity gives 0.38 similarity for A and B, and 0.32, which was what we wanted, right? If we go back to Jacob showed that it was 1 by 5 and 2 by 4, wherein the similarity of user A and B was less, but in reality the similarity of user A and B was much more common. It's in our cosine similarity it overcomes that. You can see 0.38, which shows that user A and B are much similar compared to user A and C. The problem with cosine similarity is when you apply zero, when we apply zero to the non-watched film, it means that the user has rated negative, and we don't want to create negative data which doesn't really exist. So there exists a hack for this. There exists a similarity matrix which is known as centered cosine similarity. Now, what does the centered cosine similarity does is, let's say if I add zeros over here, just a second. Okay, in this matrix, if I add zeros, and now a performance calculation based, like this is user A, I will sum up all those numbers that exist, all those ratings that user A has given, which is 4 plus 5 plus 1, which is 10, 10 by 3. This is the first data that we get from center cosine similarity. Similarly, we will perform the same with our user B, 5 plus 5 plus 4. Let's say if there's 0, it won't bother us this time because we are taking the weighted average of our table. Okay, so yeah, we take this similarity distance. Now, what we do is we subtract these values individually to make it clear. Alright. Okay, so what we did over here is we subtracted 10 by 3 minus the rating given by this user. What it returns us is 2 by 3. You can try this in your books if you have. Similarly, you can see it has rated the movie 5 by 3 minus 10 by 3. It represents you the complete opposite. Let's say if user has given low score to a particular movie, it is giving the values in negative, in minus. So we know that the user didn't like the movie. If user has given 5, so it is giving a higher value to us. Now, in our previous cosine similarity, we saw that negative reviews affect our system, but it really gave us the true values for between the similarity of user A and user B, similarity of users A and similarity of user C. What center cosine similarity will do is, okay, now you can see that user A and user B have a much similar taste in terms of center cosine similarity, which is 0.09, and user A and C do not have similar taste, which is minus 0.56. Once again, if we look at user A and user C, user A and user C, we see that user A didn't like movie 4, which he rated as 5, and C rated as 2. User A didn't like movie 5, which he rated 1, and user C rated the same movie 4. So both of these users are having completely opposite uh, taste in their movie preferences. And according to central cosine similarity, we can see that similarity metrics that a user A and user B had is 0.09, which is positive integer, and similarity of A and C is in negative, which will be discarded because it's negative value and we don't deal with negative values. So now, after knowing that which movie should be recommended to the other user, or there exists a similarity between two users, we need to predict the ratings. Let's say uh, user A didn't saw the movie 2, but user B has seen. Should we recommend user A the movie 2 or not? And if we recommend the user movie 2, what rating will the user give it? It is important. You will see the similar kinds of algorithms in Netflix, but with a bit of complications in them. Now, to predict the user, they will we will rate out their filters. Okay. Now, we'll work on this smaller data sets at the moment, A and B. There are two users, and these are their ratings. We will be representing them in a vector space. All right. So, if we talk about the user A and represent its data in vector, we'll get 4, 0, 0, 5, 1, 0. What a vector is really all the ratings given by user A. That's it. Now, we'll find n users which have similar taste as A. We will apply center cosine to them. Center cosine. If you don't really get this concept at the moment, don't worry. I will be sharing the PPTs with you guys, and you can perform the calculations by yourself, and it will be easy for you guys. All right. Now we'll find similar users that have interest like same same ones of user A and their taste, with only those users who have liked the same film. Let's say user A and B, they have liked the same film, movie 1, but none other. So we would discard this one, and we would add other users which have much more similar users and item ratings. Now rating prediction. Uh, what we do here is we take the average rating from n users wherein they have similar taste compared to user A. But going through this approach, it won't really give us the output where whether both the items are same or not. At this moment, we are doing user-user collaborative filtering. There exists item-item collaborative filtering. We will study about that also. The other way around is we will take n users and take every user and check whether their rating given to a movie compared with A's rating by taking their weighted average. Uh, we'll follow a small example for this to be clear. Up till now, we were seeing similar users, user A and user B, if they have similar taste or not, we will be recommending a movie or not. Now we will be doing item-item collaborative filtering, wherein we will check whether an item is similar to the next item, and then it will be recommended to a user. For item A, we will find a similar item. Let's say Iron Man. At this moment, Iron Man is an item for us, and the similar items that we see will be Avengers, Spider-Man, or all the Marvel movies. So there exists some kind of similarity in all these items. We will predict the rating of item A based on the similar item. According to Iron Man, the ratings of Iron Man and the ratings of Spider-Man, the ratings of Avengers, they will be similar. Almost all the all the Marvel films have a similar ratings in them. And then at the end, we will perform the same metric calculations and prediction, the Jacobian cosine and center cosine similarities, as we did in our user collaborative filtering. Now let's start this. Okay, so this is a larger data set at this moment. We have movies in our columns and users in our rows. Uh, there exists sparsity in this table. By sparsity, it means when there doesn't exist data, let's say user 1 hasn't seen movie 2, so this is a sparse. Now, when you compress this together in a matrix, you call it a sparse matrix or CSR matrix. I know these terms are new to you, but someday when you study about this, you will be familiar about it. Now, we need to find whether uh, movie 5, and user 1, what will user 1 rate movie 5 if he hasn't seen it? Now, we'll find the similarity, whether user 1 will like it or not, as done earlier. We find out that user 1 has a similarity matrix of 1 because it has been compared with user 1 itself. Now, user 1 will be compared with user 3, and they both have similarity of 0.41. They both have same taste. And user 1 and user 6 have a similarity of 0.59. Now, based on this, how can we estimate whether we should recommend this movie to user 1 and what will be the rating that the user 1 will give to the movie 5? So, S13 is our user 1, movie 1 with user 3's rating and user's 5th. So, their similarity is 0.41 and 0.59, which means user 1 and user 3, user 5 are similar, wherein user 3 has 0.41 and user 5 has 0.59 similarity. We put this in our equation and we get 2.6. This is a simple formula wherein you take the similarity of user 3 and multiply it with the rating that user 3 has given to movie 5. Similarly, we go on user 6, we take its matrix, which is 0.59, multiplied by the rating that it has given to movie 5, divided by the average of both these similarities. We get 2.6. So if we recommend this user 1, movie 5, the user 1 will rate the movie 2.6 based on our calculations. So if a user gives a positive review, then we should definitely recommend the movie to it. And also we know that the user has a positive, impact for the movie. All right. So at this moment, we have covered up the basics of how does the recommendation system work. It is a very basic recommendation system. The machine learning follows the simple approach wherein you take a model. Model is the program where you insert data and it creates, the generalized solution and gives you the output. Again, the same question: how far is Ahmedabad from Vadodara, and how far is Bharuch from Vadodara? Bharuch is closer because the distance is closer. So we put the model outputs some data, and then there exists a function which will say whether the particular output is needed or not, whether there exists a distance larger than the needed or not. And then we apply optimization algorithms. There exist several. We hypertune their parameters. We play with the parameters. The function has several parameters that affect the model's training accuracy. Thank you. If you guys have any questions at the moment, you can ask in the comment section and let the moderator know.
Okay, see, just few questions I've received on in Facebook, and many of them I've received on WhatsApp, right, from students personally. So one of the students on Facebook has asked that we saw various models like Manhattan distance, cosine similarity. Which of these
Okay.
models will be most suitable when we want to do classification of data like we did right now?
Which were the metrics, sir? Hello.
We saw various types of methods that help
Okay.
us to understand the similarity, like Manhattan distance, cosine similarity.
Huh.
So the question is, which of them is the best to use for classification?
Okay. The thing exists with the distance metric is, just a second. Let me open it. Mm, is it content collaborative? Okay. So you know, if we go back to the name Manhattan distance, why Manhattan? It is because in New York City there exists grid column structure, wherein rows and columns, wherein the city is divided in rows and columns. And similarly, in machine learning, when we do classification, wherein we require
Your
grid-like
voice is
structures.
breaking, sir.
Okay. Hello. Okay, guys.
Uh,
So,
Repeat the answer. Your voice was breaking.
okay. Uh, what we mean by Manhattan distance is the word Manhattan is a city in New York, and it's a all right. So the entire city, the entire New York City, is divided in blocks. Like you can understand, you can keep in mind like rows and columns. And if you say someone like, I want to go to Street Avenue or some Park Avenues, he will say, move 4 blocks straight, take 2 left blocks, and take 3 right blocks. What it means is the distance is calculated in blocks. Similarly, Manhattan distance in machine learning means when you work on grid-like structure, uh, where there are 2 points in particular grids. Let's say, let me draw this table. Just a second. Okay, let's say this is a grid-like structure in your machine learning, the problem that you're working with, and you receive some inputs like this. Now, based on your formulation, your rows represent some particular distance and your columns represent some similarities. You need to find whether this particular uh, information that you gain is similar to this particular information. You apply Manhattan because it exists in a grid-like structure where where there exists similarity and the data pattern. About uh, Jacobian and Euclidean distance, uh, there exist several applications. We will see like today we saw Jacquard distance, cosine similarity, and central cosine similarity. Their distance for the particular, just again, uh, their distance for particular users are similar or not. According to applications, you will see whether to use Manhattan, Euclidean, or cosine similarity. Cosine similarity works between two or more uh, vectors in a space. You can say this. We apply cosine similarity between two vectors to find whether the angle between both the lines is larger or not. Uh, it works in high dimensional space or geometric institutions. To see more about this, you can look about geometric intuitions of how Manhattan works, how Euclidean works, and then it will be clear whether to use it or not. So, hello. I think left the meeting. Just a second, guys. Just hold on. Let our moderator be back. Just a second, guys.
Hello, Yash, can you hear me?
Yes, sir.
Okay, so the next question was, sorry, I got disconnected due to internet issues.
Yes, okay.
Uh, One of the students asked that when we were calculating the cosine similarity,
Okay.
we got negative distance, right? So
Okay.
even though we might be discarding that, what is the meaning of that negative value of cosine distance? And
Okay.
other question also I'll tell you in case I face another network issue. Other question is, which are can you name some scenarios or problems to which we can apply recommendation system? And other is, where can I find data on which I can practice implementing recommendation system?
All right. So for the first question, according to sir, is why there exists negative cosine similarity. Okay. Uh, if we see for cosine, you see we got the metric similarity for A and B is 0.38 and metric similarity for A and C is 0.32. The problem was, just a second, guys. The problem was that user A and user C aren't really having the same taste. Because they have watched the same film, the Jacobian distance and cosine similarity compared them as having same taste. But you can see, let's say user A is someone with 5 years or 10 years of age, and user C is someone with 35 or 40 years of age. And movie 4 is an animated movie, and movie 5 is also an animated movie. User A tends to like it, but he doesn't like the movie, which is quite serious one. All right, user C doesn't like the animated movie, so he gives lesser marks, lesser rating to it, and user C likes the movie 5 because according to him it's good. Now what happens is in a cosine similarity, although both the users, user A B and user A C, they had different in their opinion, yet cosine similarity resulted in 0.38 and 0.32 similarity, which is approximately close. And according to us, we can see that user A and user C do not have any similarities in their movie taste. They are opposite. This is user A is a kid with 5 years or 10 years of age, and user C is a person with 30 or 35 years of age. So there doesn't exist similar taste in both of them. To discard this, we used centered cosine similarity or weighted average one, and we received a value wherein the similarity shows that they are 0.09 similar, or it can also be said that out of 100, 9 traits match with user A and user B, and out of 100, or we can say the user C and user A do not have similar tastes at all because user A is a kid with 5 or 10 age. Hello,
क्या बोला मम्मी ने तूने मेहंदी लगवाई तो मैंने को बोला था क्या हुई
ma'am, your audio is on.
Sorry, continue.
All right. So now the question was why negative similarity? Negative similarity shows that they are completely opposite. Minus, let's say, according to our this little graph, we can see vector A and vector B are similar, and so there exists a 30-degree angle between them. But if the angle goes negative, what you will say is that they are completely opposite. They are mutually opposite to each other. You cannot say that a 5-year-old kid and a 30-year-old person will have the same movie taste. So that's why negative. Negative shows that they are completely opposite, and the preference will be changed according to the age group. All right. Uh, what was the second question, sir?
Uh, could you tell some scenarios to which we can apply recommender systems to understand more about them?
Okay. Uh, YouTube. YouTube is a place where you will see recommendation according to your clicks. If you watch a stand-up comedy, then the next recommendation will definitely be a stand-up comedy. If you watch a song, the next recommendation will definitely be a song. All right. So let's say uh, we are working on a college filtering system. When we will be filtering college, and we'll be finding which college is suited according to your interest, your career that you are going to select, and your region. You can apply a recommender system to such places. Recommender system doesn't really give you single output. It will give you multiple outputs. If I search for a particular college, I will be getting multiple colleges per university, MS, several other universities. So it's important for a recommender system to distinguish numbers in 0.09 or in percentage, in point percentage, because there exist so many features in a data set. Hello.
Okay. I guess the nature of question was in asking, they're asking for some project ideas that they can use to implement.
Okay, okay, okay. So for this, we'll be seeing this short example. Okay. Uh, in this example, we will be creating a movie recommendation system. Here we will input a string, let's say Iron Man, and we will find similar movies in our data set, and it will be recommended to us. Okay, so first let's import some packages, and also we are having we are using movie lens data set. You can see this on Kaggle. At this moment, we are using smaller data set because the larger one has 10 lakhs or even more features, which are these many movies in it, and we cannot afford the computation power at this moment. So now uh, we have taken a movie variable and a rating variable. We read the CSV file, and we print the first few rows of the movies and ratings. The movie CSV file contains this title. Just a second, let me. Okay. So the movie CSV file contains all the movies with movie ID, title, and their genre. Toy Story is a animation film with the genre, yeah, adventurous animation, children, comedy, fantasy. Ratings. In ratings, you can see we have user with their IDs. Each movie and each user has been assigned a particular ID and their ratings. Timestamp is just the time at which time they gave the ratings. Now, if we see, we cannot really say whether user one has seen movie two or not. So what we do is we will fill none values. None value means that if user one hasn't seen movie two, so we will fill none values or none objects to it to say to clear our confusion whether a person has seen a movie or not. While programming, we cannot use or deal with none. So instead of none, we replace the values with zeros. So now, earlier we had none at the places where the user didn't saw the movie. And now we have pushed zeros in all those rows and columns where users and the column do not match. Now, we won't go much into the coding part, but the thing is, all we want is recommending a movie based on our string input. So this is a small graph that depicts whether how many users have actually rated a movie out of this all. This is the height. The y-axis represents number of users which have voted, and the x-axis represents the number of movies that are in this data set. The threshold value for this is, if I'm not wrong, okay. Just a second. Okay, so we have changed the threshold value to 10 right now, and you can see you can now clearly distinguish whether the particular movies have been voted by user or not. Let's say this particular section is a particular animated film that has been rated the most, or this particular section is a comedy film that has been rated the most. So it helps based on your threshold values that you set. Okay. We saw the sparsity, right, in one of our examples that a table stays sparse. It is sparse. We can say it. The table is our table is sparse at this moment because it contains number of zeros more as compared to the positive values. And there exists CSI matrix, which is sparsity dense matrix, where you see based on zeros you will be finding the positive numbers. So now the sparsity, it shows that there exists 73% of the table is sparse. We have converted into a CSI matrix. 0 2 shows which position are we storing the number. Let's say 0 2 has the number 3 stored, 1 0 has the number 4 stored. Sparse matrix is useful for uh, taking back a number from a sparse table or sparse matrix. For this particular notebook, we are using k nearest neighbors. K nearest neighbor is just a second. Let us show you this. K nearest neighbor is where you form clusters of similar vectors in a high-dimensional space. This particular group has similar taste. This particular group has a similar taste. So KNN helps in clustering the users. And after clustering, we will be applying cosine distance. You can see we applied cosine matrix and KNN algorithm. The neighbor size that we are choosing at this moment is 20. It will form a cluster size of 20 neighbors. This is a function which tells whether the movie ID and the ratings are preferable based on our input or not. Let's say after doing all this pre-processing and steps, we input the movie name Iron Man to it. It shows it shows the movie Up, Guardians of the Galaxy, Watchmen, Star Trek. All these films are sci-fi films and animated ones. So you can see the distance is 0.3688, which is 36%. They have similarities in them, and the user will be recommended these movies. Forrest Gump, another classical American movie. According to Forrest Gump, if we search this movie, it was released in 1995, and according to Forrest Gump, it is one of the highest rated movies, and it was released back in 1995. So it is showing us all those movies that were released in 19th century, and also with the ratings similar to Forrest Gump. So this is one of the examples that how you can apply your own movie recommendation system. If you go to Kaggle and you search for Netflix movie recommendation, so you will see there exists plenty of data, and also there exists notebooks. Notebooks similar to this. This is a notebook. Yeah, it works in Jupyter and Colab as well. You will find all the data set over here and the explanation what they did in each of these steps. If you want to practice more about how to make your own recommendation system or how to work with machine learning, Kaggle is the best place to get started. I think so. That should answer your question.
Yes, actually, you covered the last question as well.
Okay.
You answered the last question where they were asking about how they can find out data set and some sample program.
Oh, yes,
So
I just wanted to demonstrate how they can
I
work
guess
with.
since there are no further questions,
All right.
sorry, please continue.
Hey, sorry, Sada.
Okay, fine. I guess there are no further questions. So thank you. With this, we can end the.
I think Sir has. Yes.
I am very thankful to you for your time. Uh,
Thank you so much, sir.
I'm pretty sure the session has been very insightful for everyone. Once again, on behalf of CSE Department PIT, I would like to thank you for your time that you have given. And I guess with this, we can end the session. Thank you very much for your time.
Thank you so much, guys. Thank you, sir, for having me. Thank you, Par University, for conducting such a wonderful webinar. Thank you so much, guys.